This is a quick video for DNA replication, and there's some things you need to remember. You should remember that DNA is read in the 3' to 5' direction. So that's red, if you can read that. And then it's made in the 5' to 3' direction. Don't forget that DNA runs anti-parallel to itself. So there'll be one strand that starts at the 3' end and ends at the 5' end. And there'll be another strand that does the opposite. It starts at the 3' end on the right over there and ends at the 5' end over here. Now, a replication fork is a large separation of the DNA. It's unwound by gyrases, and you have, well, gyrases have a tendency to put it back, but helicases have a tendency to unwind the DNA, and then gyrases can rewind the DNA. So you have a lot of helicases that will unwind this large replication fork, but in order to hold it open, you have certain proteins, and I'm just going to put a few X's on there, that represent single-stranded binding proteins. Single-stranded binding proteins are great little things for keeping that replication fork open. Now, the next thing that's going to happen is you're going to have to lay down primers. And primers inside the cell are going to be RNA based. Sorry, I'm still trying to learn this pen. The primers are going to be laid down by an enzyme called an RNA polymerase. That's an enzyme that makes polymers of RNA. That's an ASE. They will lay down one primer in this leading strand. This is called the leading strand. That's because it's chasing the helicase as it unwinds the DNA. And as it chases it, that allows the next thing to happen, which is a DNA polymerase that comes on. It kind of wipes away the single-stranded binding proteins. They'll be knocked off when the DNA polymerase binds. The DNA polymerase will bind to that, and it will start laying down a copy of the DNA strand in the same direction that it's being unwound. So you really only need the one primer over here to make that work. I just want to circle that real quick. Now, the problem with the other strand is, now, let me go back and show something that's really important. That is that this mother strand that it's reading from, this is the 3' end. So that means this is the 5' end of the daughter strand that's being made in here. On the opposite side, you've got to lay down multiple primers because the DNA is being unwound behind the direction that you need to be making. So what would happen is a DNA polymerase, and an RNA polymerase would lay down the primer. A DNA polymerase will come in and it will make a copy of the DNA that goes between each of these sections. And then this would continue to open up in that direction. And what it's going to do is open up, and then you have to lay down another primer and make the pieces. These sections are called the Okazaki this pen doesn't want to work. Fragments. So that's the basic way that DNA replication occurs. You have DNA polymerase going in, laying down the daughter strands. In the case of the Okazaki fragments, then you would have a ligase. Let's change the color of this one more time. So that the ligase is going to come in and it's not doing it. It's going to come in and erase or lay down. It's not. Anyway, it's going to erase those little red sections here. And as it does that, it's going to erase the RNAs and it's going to fill in with DNA. And ligase is a much smaller polymerase, so it has the ability to make that final connection between those two fragments of DNA. That's a quick overview. There's a lot more detail in your book. They talk about the multiple different kinds. But this is the basic principle of DNA replication. It reads in 3' to 5', makes 5' to 3'. It uses RNA primers to set down. Now, if you're doing PCR uses DNA primer sets. The reason is DNA is much more stable. You can use those better in a laboratory situation than you could with an RNA-based situation.